whiteboard up. All right, good to go. Fern and Michaela, are you hearing me?
Yes, sir.
Yeah.
Okay, good. All right, so we're going to be starting sequences. We're going to do a bit of writing first, and then we'll do some examples. It's going to be a little similar to Cal 1, where you had the limits and the proof of the limits, the epsilon and the delta. Well, epsilon really, but I'm using the delta this time to prove in sequences. All right, but I'm also going to make sure you understand what it means for the limit of something and proof of the limit, what the limit is proving. All right, we have some notes to get through. So the topic is sequences and series, but we're doing the sequences first. Sequences and series. You can write the words. By the time I finish writing it, won't even look good much less. So sequences and series. The first part we'll be looking at will be sequences and limits. The limits of sequences. So let me get you through some notes and then we can start some proofs. All right, first thing, a sequence of real numbers. It's a definition of sequence. Sequence of real numbers is a function x such that is a function x such that no, let me not say anything. How would you say this? I think I just wrote on the board. I said such that because I wanted to put the colon, but it's not necessarily going to be read that way. So what do you think that would be saying? It's a function, and after function you have that right there. Remember how that is read? Anybody remember? We did this last month. If it's not last month, it's the month before. Last month is September. Yes, last month. Anyway, it's a function x mapping natural number to a real number. Or mapping natural numbers to real numbers. That's what it's saying. Continuing, so full stop after the R. Instead of, after the full stop, instead of x of n, so the x bracket n, we usually denote, we usually denote the nth element, in the sequence by x sub n. By the way, those are common x's. I keep writing capital because, you know, on this board is not so easy to write common. Let's see there. It should actually be common x sub n. All x's so far are common. So instead of x of n, we usually denote the nth element in the sequence by x sub n. Oh, German is coming. Right. And if you want full stop, more precisely.
Sir, good morning. Sir, this is the first thing?
Yeah.
All right, thank you.
What was the last thing I said? What's the last thing you guys wrote down?
More precisely.
Right, more precisely. We use this. So let me try to draw properly. We use x sub n from n equal 1 to infinity. Yes. To denote a sequence. More precisely, we use that thing I just wrote a while ago. X sub n from 1 to infinity to denote a sequence. Because you see the ends, the ends have to be natural numbers. So 1, 2, 3. You don't write x sub 0. Right, x sub 1, x sub 2, 3, 4. Because it gives you the first, the second, the third, and fourth and third terms in the sequence and so forth. They don't write x sub half, like you don't want to find the half term in the sequence. It's 1, second term, first term, third term, fourth term, fifth term, and so forth. Anyway, you guys know it already. X, a sequence x sub n, a sequence, put it like this in brackets, x sub n, a sequence x sub n is bounded if there exists a b, capital B, a sequence x sub n, in brackets, is bounded if there exists a capital B, that's B for bounded, in R such that the absolute value of the sequence is less than or equal to B. So a sequence x sub is bounded if there exists a B in R such that absolute value x sub n is less than or equal to that capital B for all n in N. So for all natural numbers. You notice they use absolute value because if a sequence gets if it gets negative, it still will be able to find a value that it is less than or equal to. Whether it's positive, well, you see. I want to confuse it. Because it can be going downward instead of upward as well. Sequence doesn't have to be getting larger. It can be getting smaller. All right. I want to get all these out of the way. I think I have 3 more. Or is it 2 more? Oh. All right, next. Because I have to do convergence as well. Next definition. This is the definition of convergence now. A sequence x sub n in brackets again. A sequence x sub n. The reason they put the bracket around it is because it's a set of numbers that you get from the sequence. A sequence x sub n in brackets is said to converge to a number x, is said to converge to a number x. Should I use L? No. You write x already? No, if you use L, I prefer L because x might confuse me before. It's said to converge to a number L. Use capital L. In R, the sequence x sub n is said to converge to a number L in R if, here's where it gets technical now, up to calculus, if for every epsilon greater than 0, there exists an m in natural numbers, or there exists a natural number m. That's the next way to say it. There exists an m, capital M, in the natural number set. So it's capital N right here. Oh, that's men. Cool. There is an m in n such that, space, such that the absolute value of x sub n minus L is less than epsilon. for all read it again. There exists an M mango in N, as in never, capital N, such that absolute value x sub n minus L is less than epsilon for all n, common n greater than or equal to m. I'll explain that soon. Let's write it down. There exists an M in N such that x sub n minus L absolute value is less than epsilon for all n greater than or equal to m. Full stop. The number L, the capital L that we just wrote a while ago, this one right here, number L is said to be the limit of this sequence. The number L, capital L, is said to be the limit of that x sub n in brackets. And is written as limit as n tends to infinity of the sequence is equal to L. It should start looking a lot like what you learned in Cal 1. So I'm hoping you learn it in Cal 1. Who taught you Cal 1, Anthony?
Miss Granville.
Or who taught? Well, let me learn it then. I'm sure that you're not missing anything. Who taught you, Lafern?
Miss Granville as well.
Praise the Lord. Michaela?
Mr. Campbell.
Oh, I'm not missing anything either. Hyatt, who taught you?
Dr. Wilson.
Dr. Simpson?
Yes, sir.
Oh, Lord mercy, I hope it didn't. Anyway, let's see, look. Because he tends to teach a little bit extra and sometimes miss the basics. But all right. All right, so you know what? Let me not take it for granted. Let me show it to you. How this thing works. Because you might be called upon to explain it. All right. So let me go through the note, everything we said a while ago. So the sequence is said to converge to a number x, to a number L. All right. This means as this. Show you everything I'm talking about. Let's see, this is the limit as n tends to infinity. Sequence here is equal to L. So as n, common n, because we have this sequence, we're going to have x1, x2, x3, x4, and so forth. As this gets larger and larger and larger, the value for the n, as that gets larger, we want the sequence to be going towards a particular value, which we call L. So if you were to draw it graphically, look at what we said a while ago. Let me go through everything that we said. So we mentioned that, well, I might need more space than this. Sorry about that. Let me redraw it. I already told you this first part a while ago. As the n gets larger and larger, we want the limit to be going towards a particular value, which we call L. So it's converging towards that value. If you were to put this in a graph here, let's say for the smaller values, let's say we have the 1 here, 2 here. So x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and so forth, and blah, blah, blah. 6, let me make it longer. 7, 8. So this is here, and then 2 is there, and then 3 is here, and then 4 is there, and then 5 is here. Closer. 6 is coming there, and 7 is coming here. So as the values for x are getting larger, you realize that, or you should be able to realize that we are going towards a particular value here on the y-axis. which is where the sequence value will be. So the values on the x-axis will be the ends. So you have x1, x2, x3, x4. The results are on the y-axis here. In other words, let me circle and see what I'm talking about. This one right here will be x sub 1, that will be x sub 2, c sub over 2, x sub 3, and so forth. But as you can see, it's going close and close to the line right there, which is where our L will be, right here. Now, this proof that we're going to be doing, or this definition, is what we're going to be using to prove that the limit is equal to a specific value. Let me explain to you what they're saying. Notice I said that for every epsilon greater than 0. No, we want the epsilon to become as small as we can possibly make it. Any small number, even though it says epsilon greater than 0, you're not going to pick any random number like 1,000,000 or 2,000 or a big number. You want to get the number as small as possible. Because if you notice here, you have x sub n minus x, sorry, L. I forgot to change it to L. Let me see. X sub n minus L less than epsilon. So no matter how small you make that value epsilon, you want it to be such that the distance between the limit L and the sequence values are so small. No matter how small you want to make that epsilon, you can show that it's going closer and closer towards that limit. In other words, the distance between xn and L is getting so small that no matter how small you want to make that epsilon, that distance can be smaller than it. In other words, it's going that close to it. So if I put epsilon as 0.01, you can show that there is some value m in the natural numbers. That's where that m comes in, you know. There is some value that, so by the way, let me make sure you understand this. You see the bigger, not the bigger, sorry. The smaller you make this value, epsilon right here, is the larger this value m is going to have to be to show that it's going closer and closer towards the limit. Because remember, this that m right here is going to be actually x sub, this m right here. So the larger, sorry, not larger, the smaller you make the distance between the sequence and the limit by lowering that epsilon, is the larger you're going to have to make that m to fit it to show that it's going closer and closer towards the limit. So that's why I mentioned that n is going to be greater than or equal to that m. So you should be able to find an m to match any epsilon that you choose, show that it's going closer and closer towards that limit. So no matter what, no matter how small I make that epsilon, you should be able to find an m that satisfies that inequality right here. Now to do that, let me show you. Look at it graphically now. Let's say our x was say about I don't know. Let's say the x was right here. Use a different color. Let's say right here in the graph. Match our limit. Match the limit right here. Oh, whatever. Anyway. Now, if you're going to reduce the distance over here, so down here will be L minus epsilon, and up here will be L plus epsilon. If you don't know where that comes from, maybe I should show it to you first. Unless you guys know. You guys know how we move from that thing I circled to the L plus epsilon, L minus epsilon? You know how I get to that? Show the thing one, but I don't know if you guys remember how to get it. You know what that means? Yes. You know how I move from the thing I circled right there to the L plus epsilon and L minus epsilon?
From a circle?
No, the thing I circled. The thing up here. It's right here. The thing I circled
Oh.
right here. You know how I move from that to the L plus epsilon, L minus epsilon?
Yes, sir. Because remember you have L there, you know. So we have L plus epsilon. That would be the distance between L. That would be L plus that. Well, I understand it.
For sure.
Yeah, I understand.
Make sure you know what I mean. I'm saying how we can get from that to get this and get that. That's what I'm saying. It's actually called algebra. If you look at the paper, you probably figure it out.
Because it has a magnet
Absolute value.
around it,
Because what?
absolute value sign.
Right, that's exactly why. Because all right, you get it then. Remember when you remove the absolute value, you're gonna make everything you're gonna make it positive. So you care about the L, you're gonna get L minus epsilon, L plus epsilon. You have a minus epsilon and a positive epsilon. Yeah, all right. Since you say I get it. The next two are correct, so they get it too. Okay. Now what we are saying is, no matter how small amount you make that epsilon, of course, the smaller you make that epsilon, the closer you go towards the limit. So as epsilon gets smaller, let's say for example it was 1, then you make it 2, sorry, 0.5, then you make it 0.05, and then 0.01, 0.00000001. The closer you get to that L, right there, you should be able to find a value for M, and M is going to be located down here, X sub M. Because remember, the values that I put down on the x-axis represent the N in your sequence. I'm going to put X sub M right here. So you have N equal 1. As a matter of fact, I should call this the N axis if you want to call it that. Not really X axis anymore. It's the natural numbers that you get for the X, so the subsequence, for the sub values for the sequence, like X sub 1, X sub 2, X sub 3, X sub 4. You should be able to find an M to match that small interval that you place around the L. That's what you're doing when you're proving the limit of a sequence. You're showing that no matter how small you make that distance between what I wrote on the y-axis a while ago, make it bigger. No matter how small you make this distance right here around the L, you should that's what you're doing when you're proving the limit of a sequence. It's a bit, I mean, a bit abstract, but that's what you're actually doing to prove it. If you can find an M all the time, match your small epsilon, then you have proven that it's converging towards that L. Okay. So the best way to do this most of the time is to show you an example. So we're going to create. Now I'm going to show you, remember, in calculus, I just normally used to show my students how to find the epsilon, how to find M or epsilon, because you need to find a particular epsilon to match an M. You're going to use the epsilon to find an M. Now I normally show my students how to do it, but I normally show them what the proof is afterwards. So I'm going to do both of them right now because we're high enough in math. So I'm going to show you to find the value and actually to prove that is the value. So let me create a sequence right here. I'm not going to use a real sequence yet. I'm just going to create one, and then once you see how it works, and then you can apply it to real sequences. So we have a certain sequence, and we want to prove. Oops, prove that prove if the limit as n tends to infinity. So you're given the answer this time. Prove that the limit as x tends to infinity of this sequence, if it's equal to 2, then the limit, what this writing is awful. The limit as n tends to infinity of 2x minus 1, x sub n, beg your pardon, minus 1 over 3 is equal to 1. Maybe I should read it because I can't read it myself. Prove if the limit as x of sub n, sorry, prove the limit as n tends to infinity of x sub n is equal to 2, then the limit as n tends to infinity of 2x sub n minus 1 over 3 is equal to 1. Okay, right, because I'm going to have to erase it for space eventually. So I'm going to prove that if that limit is equal to 2, then the next limit, some additional things, should be equal to 1. So my advice when you're doing these, not advice, the way you should do it, the method you should use is first find the particular m that satisfies whatever epsilon you can choose. So you're going to realize that the m that you choose depends heavily on what the epsilon is. Because if I choose 0.5 and someone else choose 0.01, you're going to get different m's. You need to be specific in the epsilon that in the m that you choose. So once you have that, now the first thing you need to do, remember, in the proof, it is right over here. Squeeze it up in the corner. You want the sequence to be less than epsilon. It's all right. We know the sequence is x sub n, and the limit that you want, the limit that you have is 2. Here's something rough for it first to find a particular m that satisfies epsilon. So you want x sub n. You want x sub n. Well, sorry, not want. You are told that x sub n minus 2 is less than epsilon. Where were we told that? Can anybody tell me how I know that? How do we know that that is so? Anybody? How do we know that x sub n minus 2 is less than epsilon? Absolute value. Nobody? I cannot give away the answer now right before I started. I feel bad. Okay, definition I gave you for
Because
convergence. Okay.
oh,
Right.
well, I'm looking at this saying the limit as n approaches infinity.
Mm-hmm.
The limit is 2.
It's
So
2, right?
I'm just thinking that 2 minus 2 is 0. So epsilon have to be greater than 0.
I'll be technical now. It came straight from the definition of convergence, you know. In
Right.
convergence, it says that there exists an m such that x sub n minus the limit. As I wrote over here, so you would see it first, minus the limit. Oh, no, I messed it up. Less than epsilon. So the limit that they gave us was 2. They told us the limit was 2. So that's how I know that this must be true, right here. They told us that limit was 2, so just put 2 in it, replace the, what do you call it?
Okay.
L with 2. Yeah, that's all I did. So we're now going to use that to find our particular epsilon for particular m to match our epsilon for the thing that we want to prove. So we're going to prove that if that is the case, as we have assumed right here, then we're going to prove that the limit now of the 2 sub x sub n minus 1 over 3 is equal to 1. So we need to find a particular epsilon that satisfies that, particular m that satisfies that. So what we do now is we have a sequence which is 2x sub n minus 1 over 3. So your algebra is going to have to be good right here. Minus what they said the limit should be 1. You know what I've done? I have replaced the limit thing that we have right here in the formula. I would wrote it down. So this x sub n, our limit is now going to, our sequence is now going to be 2x sub n minus 1 over 3. So I replace that with 2x sub 1 minus 1 over 3, 2x sub n minus 1 over 3, and I replace the limit with 1. The one right here. That's how I got these things to the left right here. Put the limit in, put the sequence in there, minus, put the limit in there, and you solve until you get your particular epsilon satisfied. But you have to use what you have known to be true. You see, we know this is true right here. We have to use that. In a circle to the left, we have to use that. So we need to get it to look like that. Otherwise, you can't prove that the limit of the next one is that to the left. So let's continue. This would be equal to, I'm going to go as slowly as possible to make sure you understand it. 2x sub n minus 1 over 3. Fix up that 1. That 1 will also be 3 over 3, the same way you call it, same denominator. So that is 2x sub n minus 1 minus 3. So since I have the same denominator, we can subtract. That's now 2x sub n minus 4 over 3. Good so far? What am I writing? Bad enough. Whatever. So I'm in the complaints, so continuing. I'm going to now factor out the 2. Matter of fact, factor out the 3 as well. Matter of fact, let me ask you guys. When you factor out 2 over 3, what is left inside the absolute value? You will do it. Nice that way.
xn minus 2.
Praise the Lord, sister. X sub n minus 2. That's absolute value at n here. And it's so close to the edge of the board, I can't write it. After the 2, there's a bar. So remember, all along, that thing was less than epsilon. I hadn't been writing it, but this right here, the 2x sub n minus 1 over 3 minus 1 was less than epsilon all along. And we show that at the end, that is actually 2/3. So now I can actually put my bar at the end. Minus 2, this came from right here, less than epsilon as well. So all you have to do now is multiply both sides by 3 over 2. So we get x sub n minus 2 must always be less than 3 over 2 and whatever epsilon you choose. So you see that 3 over 2 epsilon, that's going to be the m that we use. You're going to see it makes sense as we go along now. In the proof. All we've done so far now is find out what the m is going to be in our proof. So we have figured out what we're going to use for m. So this is how you're going to start proving that a sequence converges to a particular value, which is actually the limit. Whether it converges to is actually the limit of the function. If it doesn't converge, it doesn't have a limit. Hope you realize that too. That's what definition said. Once it converges to a particular L. That L is the limit. If it doesn't have a limit, it's not converging. Okay. So what I've done right here is figure out what I'll be using for m. I'll be using 3 over 2 epsilon as the m all the time. Because xn minus 2 must always be less than 3 over 2 epsilon. So write that off, and then I'm going to now do the formal proof. So I have not proved anything yet, and all I've done is find the m that I'm going to be using.
Sir, you said you found the M?
The m that we'll be using. Remember they said that the proof, let me see if I can go back and read it. I have my books right here. Oh, a sequence is said to converge to a number L if for every positive epsilon, that's what you can read, epsilon greater than 0 as positive epsilon, there exists an m. So our job was to find that m. We have found it now. So this thing right here, let me circle it, is the m that we'll be using. So it's a bit technical now. Actually trying to find the m. And once you found the m, you're going to use it in the proof. So when you finish writing, let me know and I'll show you what the proof is going to be. The more I do, the more you get used to it. So don't worry. You might look a little technical at first because I know you forget some of the stuff in Cal 1. All right. Anyone else still writing?
Yes, sir.
No, sir.
When you finish, let me know.
Sir, when you circle the 3 over 2 with epsilon, that represents m?
Yeah, that's the m that we'll be using. When you do this part right here, this portion, this is what they call rough work. Some people call it scratch work. Is what they use to find your m. Once you have found the m, you use it in the proof. Because you haven't proven anything yet, all we've done is found the m. You're going to see the proof now.
Okay, sir.
Finished, sir.
All right. So we want to show that I'm going to erase this now, So remember, we wanted to show that this limit, look up at the top, I'm going to circle what we want to show. We want to prove that this limit right here is equal to 1. And by doing so, let me read the proof again. Let me read the thing I want to show again. To show that that limit is equal to 1, we need to show that there exists a particular m, natural number m, because you know m is in n, a particular m, let me say it a different way, a particular natural number m, such that this difference right here in the absolute value, what I'm circling. If you look back at the proof, look at the words and the proof, I'm sure there's a particular m that satisfies that absolute value difference, if you want to call it that, less than e. Let me say it again. I think I might have confused it a while ago. We want to show that for every positive epsilon, there exists an m we have just found that will make sure that this difference right here is less than epsilon. All right, so we're going to go back to right to this one right here, and we use that m that we just found a while ago. All of them know. So here's the proof now. When you're doing the proof, show me the factorial and show me the proof as well, so that at least I know that you know how to find the m. Let's clear the proof now. Why is it not clearing? Ah, there we go. So here's how you'd write the proof. We'll start by saying let epsilon, oh geez, yeah, the positive number. Then there are other stuff you can say, but I can't bother kill you with those. Because you could have got to writing the whole thing again, but it's not bother with that. So let epsilon greater than 0. Then for all, you guys know the symbol right here? Upside down V with the thing through it. Right again. You guys know that symbol?
Yes, sir.
What do you mean?
No, sir.
For all.
Right, it means for all. I'm writing for all. So it means for all. The upside down V, a matter of fact, upside down capital A. Yeah. Means for all. I'm right in the corner here, so I see properly. That means for all. All right. So for if we let epsilon be a positive number, then for all n greater than m, capital M, here we go now. 2x sub n minus 1 over 3. Remember, that's what I want to prove is equal to 1 minus the particular limit is equal to 2x sub n minus 1 over 3 minus 3 over 3, which is equal to 2, oops, for the 30. Oh, yeah, 2x sub n minus 4 over 3. I'm going in steps, which is equal to, oh Lord, suppose the factor with 2/3. 2/3. Oh, that doesn't look bad. 2/3 x sub n minus 2, which is now going to be less than 3 over 2 epsilon. That is the end that we want to be less than that all the time. But we have, I'm not talking right over here. We have just shown that 2/3. We have, remember this thing is our m, you know. 2/3 x sub n minus 2 is less than 3 over 2 epsilon. That's the end that we are using. But we actually need to show that this matches what we have been told is true. We have been told, multiply both sides by 3 over 2, that x sub n minus 2 is less than 3 over 2 times put the 2/3 right here. Oops. Now, it's up at the top. But it's already the 2/3 right here, right at this point right here, so we know that x sub n minus 2 is less than what? We were told at the start, x sub n minus 2 is less than
Epsilom.
Epsilon. So if x sub n minus 2 is less than epsilon, and we have used m, capital N, capital M, beg pardon, as 3/2 epsilon, then that's our m, you know. We are using that x sub n minus 2 is always going to be less than, we have used m as 3/2 epsilon. 3/2 epsilon right here. Then that would mean that this right here would be equal to 3/2 epsilon. Remember, look at this down here, down the bottom part right here, using 3/2 epsilon. If that is less than 3/2 epsilon all the time, that's our m that we're using. When you multiply it by 2/3, we're getting epsilon right here. So that means that if xn minus 2 is less than 3/2 epsilon all the time, then 2/3 times xn minus 2 will always be less than epsilon as well, because it's equal to that. We have used m as 3/2 epsilon. That's the m that's always going to be less than or equal to, less than, what we have used is 3/2 epsilon. It's always less than that. So because 3/2 epsilon is our m and it's always in it, then when you multiply by the 2/3 right here, which gives us this right here, we get our epsilon back. So you have to find m first, so that when you work out this thing and multiply it, you get by the epsilon that you want to get. And for any epsilon, it will always be less than it because of that. As I said before, it's a bit abstract. When you do more of them, and probably if I use an actual sequence, it'll make more sense. But this is for the general sequence. It works for anything. Find m first, work out your thing, then you choose that m, put it back in there. When you multiply it, when you work it out and multiply it, you get back an epsilon all the time. And because you've shown that it's less than that epsilon all the time, any epsilon, because that e represents any number right now, you know, and it will always be less than it because we have used m as 3/2 epsilon. So therefore, it will always be less than epsilon. All right, no question. So good to go.
Sir, we first assume so we understand, right?
I say if there are no
But when
questions,
I
it means you understand.
roughing it, sir, I don't know about it, sir. I'm going to watch by the video though.
No problem. Tell you what, let's do another one too. I'm going to sequence system. This is for a sequence. I use x sub n as a sequence.
You're breaking up, sir.
The x sub n represents, I just made up something like 2xn minus 1. But I'll show you a real sequence and see if you catch it. If you catch it, then we're good to go. If not, then we have some work. I'm waiting for you to finish writing.
Sir, is it possible for you to write it, take a picture, and upload it? Because I don't know what is taking place there.
What do you mean?
I don't see the end. Where's the answer?
The proof is that we've shown that. Look from the start. Look here. That equal to that, which is equal to this, which is equal to this right here. I tell you what. Let me write it over. Look at that. Where can I batch it to? Okay, right again. Stick with black ink. Remember, we have chosen m as 3 over 2 epsilon. So for that m a while ago. So follow me now. So 2x sub n minus, what was this? It was 1 over 3 minus 1. Yeah, because we had set the limit out to 1. Good. We want it to be less than epsilon. But at the same time, we know that we have chosen that x sub n minus 2 must be less than 3 over 2 epsilon. That's the n that we have chosen. M, capital N that we've chosen. So write that over there. And follow me now. So we want to show that this thing right here is less than epsilon. We want to show that, that this is less than epsilon by using that thing that I circle up. We want to show that 2x sub n minus 1 over 3 minus 1 absolute value is less than epsilon by x sub n minus 2 less than 3 over 2 epsilon. Good. So let's go now. So go in steps. So 2x sub n minus 1 over 3 minus 1 is equal to 2x sub n minus 1 over 3, that's n here, minus 3 over 3, which is also equal to all I'm doing so far is just rewriting stuff. I haven't changed anything. When you combine the numerators, you get 2x sub n minus 4 over 3, which is equal to factor 2/3, 2 over 3, x sub n minus 2. Let me try this in the next line. I haven't changed anything. Equal 2x, because I want to show everything properly now. So everything is the same thing that I have at the end. I want to jump it in the corner. What did we say our 2x sub n minus, sorry, x n minus 2 is absolute value? Or did you say it's, we're going to let it be less than?
Epsilon.
Sorry, I didn't hear that.
Epsilon.
Not epsilon. See, I circled up at the top, which was particular m.
3 over 2 epsilon.
3 over 2 epsilon. So this must be less than, remember we're using the thing that is less than at the top now, we're substituting it. See the 2 over 3 on the outside? It's still there. But xn minus 2 must be less than 3 over 2 epsilon. That's the m that we chose, which is equal to epsilon. So if the thing right here, we have shown that remember that is the same as this. Now all I do is rewrite it as in a different way. We have shown that is less than epsilon right here. That's what I wanted to prove. It's less than epsilon by using, we have used our m right here as 3 over 2 epsilon. It's going to be less than it all the time. So we have that is less than epsilon by picking a particular m as 3 over 2 epsilon. So if I use epsilon as 10, then 3 over 2 epsilon is 15. M is 15. If I use epsilon as 0, well, I can't use 0, must be greater than 0. If I use epsilon as 2, then m is 3. Did I get 3? 3 over 2 times epsilon. So in other words, I've shown that what epsilon I pick, I can find a particular m to match it. That's 3 over 2 times whatever epsilon I choose. This is when I always work out, no matter what value I choose. If I choose epsilon as 1000, it's simple. It's just going to be 1500. How do I get that? 1.5 times 1000. That's the purpose for finding the m first. So that no matter what epsilon I choose, I can show that thing is going to be less than it right here. That's the purpose of finding the m first. You mean a little better? You mean fall asleep?
Wait, as if it's any better?
Mm-hmm.
I'm saying I give this on an exam.
We just analysis for color.
Sir,
It's the base of your
sir.
is the base of calculus
Mhm.
sequence. Upper limits are the basis of the analysis. Yeah.
Sir, this question just now let me feel like this is the hardest question ever doing a math.
You know, to be honest with you, it's not hard. It's just so abstract that you see, because most things in math, that's why I don't like it either. Most things in math, you can say, all right, you can prove that. You see, these proofs, you know, it don't make sense to you sometimes, because you say, oh, whatever this doing, they know that this is so. Why did they prove it? That's why they used to confuse the daylight out of me. Because I'm saying, seriously, I mean, that's obvious. Why are they proving that? But let them do it. So it is their math. I'm yet to see what I'm going to use it to do, but it's a real analysis for it. Analyzing the math in detail. I think people never know how to come up with this. Maybe it's used somewhere, I don't know, but I don't see what it's used in real life.
And sir, persons pass this course?
Yes, man. I passed it at you.
What? Yes, sir.
Then how I think you're going to get the first masters in math, I can't pass this. Oh, let me tell you something though. We had this course at UA. There was a teacher that came from Cambridge, a lecturer. I think his name was Vernon. Yes, that was him. I can't remember his name. He came from Cambridge. Well, him saying come from Cambridge, and I think university employed him somewhere like he was true. The class had 42 students. By the time we reached about the third or fourth week, half of the class gone. People dropped the course. Remember, the man couldn't teach at all, you know. He just come and say, you guys should know this, you guys should know that. By the fifth week, me stopped the class. I didn't drop the course, but I stopped going to class. I was the fifth week I stopped going. I stopped going when it was when we reached a point where if you drop the course, you don't get back any money. I just stopped going to class and just focusing on other classes. I realized I couldn't pass this thing. I was not understanding nothing in the class. And then when I go to the exam, I think when I came out of the exam after about 40 minutes, 15%. I remember I asked them the grade. 15% I get for the exam. And you know what? That was the fourth highest out of the whole class. Because I understand the first part of the class, get 15%. The highest grade in the class was 37, I think, 37%. The whole class failed. They had to let us do the course over free. Because they realized that the man wasn't teaching anything. Just come and bright and, well, I don't know if him bright. He used to come to class and tremble and sweat. He's a spot in us. I realized that this man never teacher. But he actually knew the stuff, it's just that he couldn't teach it. He couldn't impart it the way that we could understand. And the whole class failed. And it came in the newspaper. If you go back and look at that year, you probably find it. The whole class failed. Because the course was so abstract, you have to, that's why when I'm showing it to you now, I don't skip any step at all. I make sure to show you that you have to first find the particular M, put it in there. When you put it, notice the M didn't come back until the N right here. Right here, this is where the M came back. And you want to, because look here, I tell you what. I remember when the teacher who taught us the second time, what he did one question about 3 times until we got it. So maybe I should do this one next time. I think I did it 2 times already. This part 2 times. So I did it one more time. And as I'm going through, I'm going to tell you what to look for. See this thing a circle up at the top right here? Use a different color. This thing a circle up here. That's the main focuses you're going to use. And right here is when it comes back. That's how we went to a while ago to find that M and to put it back right here. So, for the question again. Much time we have? 30 minutes. So maybe I have to go give you assignment Monday instead of today. Because I wanted to show you more than one. All right. The question asked us, if the limit as x tends to infinity, not mercy, that's foolishness. I don't think that's what I said. It said limit as n tends to infinity of x sub n is equal to, what was it equal to again? Oh, 2. I think it was 2. Then the limit, 2x sub n minus 1, was it 1? I think it was 1 over 3 as n tends to infinity is equal to 1. Take a books, please. Is that what I gave you? That if that, then that?
Yes, sir.
Okay. No. You see this part on the left right here? If this, that means that is given. You don't have to prove this. They tell you that this limit is equal to that. You don't have to prove that limit. You are told that that limit is equal to that. And if that is the case, that means that x sub n minus 2 must be less than epsilon. For any epsilon you want to choose. How do that? Because at all times, x sub n minus the limit of the sequence must be less than epsilon. This is something that is given. So don't forget this. X sub n minus L, absolute value, must be less than epsilon. So if you are told that the limit of a function is equal to a particular value, it means that limit of a sequence is equal to a particular value. It means that that limit, you're going to place it into this thing, a circle to the right, subtract it from the sequence, make it be less than epsilon, because you are given that. So we are given that x sub n minus 2 must be less than epsilon, absolute value. What we want to prove, look, I'm going to show what we want to get from right now. We want to be able to show that 2x sub n minus 1 over 3 minus the limit as well, that we're given, so we're given is equal to 1. We want to prove that that is less than epsilon. We want to prove that. We have to pick a particular value that will make that true by using the one to the left right here. Let's say that again. We want to pick a particular value using the thing on the left to make the thing on the right true. Say it one more time. We want to use the thing on the left we know to be true to make the one on the right side true. That is proving the limit. Okay, so let's find that value. So here's how we go about finding that value now. So we use the thing on the right now. On the right we have 2x sub n minus 1 over 3 minus 1 less than epsilon. Factor out some values. Well, I'm going to skip a step right here. I'll just show it here already. 2x sub n minus 4, that's by combining negative 1 over 3 must be less than epsilon as well. Keep factoring. Take out the 2/3. So 2/3 x sub n minus 1, 2 beg pardon, we factor out the 2/3 must be less than epsilon. That's what I want to get. Well, I want to get to the thing to the right. So now we can get what we started with. Remember, we need to use this thing up here. We need to use that at some point. So multiply both sides by 3 over 2. We have that thing a circle at the top right here. That is less than 3 over 2 epsilon. This is what we need to use to make this thing up here true. We need to use a 3 over 2 epsilon to replace the one right here to make it true. So that means that for any epsilon that we choose, 3 over 2 epsilon is the bad value that it must be less than. So I'm going to now erase this. Everybody okay with what I did so far? I kept repeating myself, so good. I'm going to now erase that, and then so we're going to use that 3 over 2 epsilon to make the thing up there that I underlined true. All right, let's see how that works out. 2x sub n minus 1 over 3 minus 1 right here, yes. came from the sequence minus the limit is equal to I'm going to do this one slowly though. I'm skipping a step for this one. Over 3 minus 3 over 3, which is equal to, combine the 3 and the negative 1 now, minus 3 minus 1. So that's 2x sub n minus 4 over 3, which is equal to, after 2/3, 2 over 3 x sub n minus 2. But if you remember the previous slide that we had, our previous board, or whatever you want to call it, before I erased it, we had shown that xn minus 2 will be less than 3 over 2 epsilon. We're going to now replace that. But remember now, if you replace it, it's now less than, because if xn minus 2 was less than it, so we replace xn minus 2 with 3 over 2 epsilon. Which means, look here, you see that 2/3 xn minus 2, 2/3 xn minus 2, we want to make sure it's less than epsilon. So we are using 3 over 2 epsilon to make sure it's less than it. So that means that this right here now is equal to epsilon, which means that this is less than that epsilon by using this value right here. So 2/3, we have shown that the big something up here, so, which is equal to the little thing down here, is less than epsilon right here. For any epsilon that you would choose, use the value that I underlined 3 times, well, underline epsilon 3 times too, to make it less than epsilon. That's the proof that we have used, shown. By using 3 over 2 epsilon, you can make, for any epsilon that you would choose, by using 3 over 2 epsilon, right here, you can make it less than it. Less than epsilon, that is. If you don't understand at least the last part, or at least you understand up to that last part right there. Very slowly, and you say you understand the first part. All I did right here was just write back the same thing that we did before, and then insert the 3 over 2 epsilon. I'm hoping that you're quiet because you understand.
It's clearer than before, sir.
Okay. What time is it? 8 minutes past. Okay. Let me show you an actual sequence. Anybody writing? I don't think so. You write this already. Wait, Lafren said she didn't understand the first part. So, I mean, she didn't know what to write. You wrote this already, Lafren?
Yes, sir, I got it now.
Okay. All right, so write this down now. Prove the sequence 1 over n. I can't write the words. Prove the sequence 1 over n. Remember, that's all right. Sequence is no. Once you set around the thing, you know it's a sequence. With the set brackets, I should say. Prove it is convergent and limit. What's going on? Oh, limit as n tends to infinity of the sequence is equal to 0. So it's going towards 0. That's what I want to prove. All right, so let's go. Should have that by now. So first, we're okay. All right, let's check what's going on. Remember, you know, it's going to be, write this again, sequence minus the limit less than epsilon. So let's find out what the m is going to be. That's always our first goal, find out what m is. So let's go. Absolute value, this is rough work first, as usual. 1 over n minus 0 is less than, don't do less than yet, let's find the m first. I know, find the m, find the epsilon. So that is less than epsilon. You need to use that to find the m. Now, remember that the values for n are natural numbers. It's going to be 1, 2, 3, 4, so forth, and whatever. So we know that, matter of fact, let me do it slowly. 1 over n minus 0 is just 1 over n. This is the point I want to get to. So we know that n, the values for n are natural numbers. So what does that tell us about 1 over n? It is always what? A p word.
Positive.
N, positive, good. So the absolute value doesn't need to be there. So that means that 1 over n must be less than epsilon. But we want to find the particular value of n that we want to work with. So what we're going to do is multiply, well, the Jamaican term, cross multiply. That will give us 1 over epsilon. N is greater than that. So for this proof to work, we're going to use 1 over epsilon as our n. I'll say that again. For this proof to work, we're going to use 1 over epsilon as our n. Sorry. You see how I got it? Do you look screeching work until you find a particular value? Like a while ago we did it, we found the value for n. Same thing we do right here, find the value for n again. Oh, by the way, this will make you understand. N, I keep saying n. M as in mango will always be something in terms of epsilon. They're solving to getting something in terms of epsilon. All right? So m is always going to be something in terms of epsilon. A while ago we had the sequence written down. But in this case, you can just solve for the epsilon by using the n. So I said when you get a particular sequence, it's easier to understand. You're solving for n. A while ago didn't really have the particular sequence. So we have the n greater than epsilon, 1 over epsilon right here. Look at how it works out nicely in the proof now. We're going to now prove that 1 over n minus 0 is less than epsilon by using that 1 over epsilon that we just had a while ago. Follow me now, follow me carefully. So we have found our n. Where is it? Right here. So 1 over n minus 0, absolute value, is equal to the absolute value of 1 over n, which is equal to 1 over n. I haven't skipped any steps so far, everything straightforward. 1 over n is a positive number, so we can remove the absolute value. But that must be less than, what did we use for n a while ago? 1 over, you tell me, what to put below the 1?
Epsilon.
Sure. Look at what n is. What we're using for n.
Oh,
Underline it 3 times. So it's not catching on quite yet. So I'm going to do some more next week. Anyway, we have, all right, look here. You see, because n must be greater than 1 over epsilon for this to work, we're going to use this right here. Think about it. If the number below the 1, I'm going to use a number over here. This is 1 over 10, and this is 1 over 3. Which number is bigger? 1 over 10 or 1 over 3?
1 over 3.
1 over 3 is bigger. And why is 1 over 3 bigger? Because 10 is bigger than 3. So the bigger the number in the denominator, the smaller the fraction. We have shown a while ago that n is bigger than 1 over epsilon. Remember we did it over here? We have shown that we're going to use n to be bigger than 1 over epsilon. N is always going to be bigger than 1 over epsilon. So okay, since n is bigger than 1 over epsilon, then that means that 1 over n must be less than 1 over 1 over epsilon. That makes sense, not true?
Yes, sir.
And what is 1 over 1 over epsilon equal to?
Epsilon.
Epsilon. So we have shown that 1 over n minus 0 is less than epsilon by using the m value, this fancy value right here, the 1 over epsilon. That's always the key, find that m. So really the first is you start out by using the thing over here, the thing that you want to prove, find a particular value, and then use that value to make your thing true, which you did right over there. It's not so intuitive at first, but when you get used to it, you're going to say, oh, not so bad. So watch these over, because each thing that you might not be grasping because it's the first time you're seeing it. With sequences, you probably saw it with I think it's easier to understand functions, you know. When I teach Kelvin, people catch it faster than this. Sequences takes a little more time. So I'll prove when I come to class next class, I'm just going to prove maybe 4 of them. Give the sequence, find the m, prove it. Give the sequence, find the m, prove it. Give the sequence, find the m, prove it. And if by that time you don't get used to it, then the exam is going to be rough.
Sir, if I get it by then, we give up math.
I wouldn't say that. I'll give up on the A.
I'll give up on
Because
it.
this question is going to be an exam. Or these questions, maybe 2 of them.
Okay.
Yeah. All right, so my advice to you guys, watch these again. Watch the 2 of them, the 2 that are proved, and you're going to hopefully pick up the pattern. Next class, I'll do some more, so don't worry about it. The one I give you first, maybe I shouldn't have done it first. I shouldn't have done it at all because it's a general proof. And you don't realize that. Because I think some of you might be, well, there's 4 of you. Some of you, maybe one of you might be saying, but this time I found n a while ago, I found the xn minus 2. What's Sarah doing? It look different. Focus on this last one. Because the ones that you're going to get on the test or the exam are going to look like this last one. You solve for the n. Don't be frightened. So I said this is actually easy when you do a sequence, because if I show you this first one, you solve for the n, and then show you the next one, you solve for the n again, you say, oh, that's not hard. And you put it back in your thing. But the thing about this, you have to use like a common sense. See, because, let me show you the 2 key things about this proof, this particular one. See, because we know that n, thing a circle, let me show you again right here. Point to it. We're looking at this part right here. Because we know that n is a bigger number than 1 over epsilon, then this part right here now was key. Because n is bigger than 1 over epsilon, 1 over n must be less than 1 over 1 over epsilon. The same thing I showed the fractions down here. The bigger the number in the denominator, the smaller the fraction. So because n is bigger, it must have been smaller than 1 over 1 over epsilon, which makes it smaller than epsilon, which makes 1 over n smaller than epsilon, which is what I wanted to prove from morning. Anyway, so that's where like a common sense comes in. Well, I shouldn't say common sense. A little analysis comes in. But apart from that, it's straightforward. And as all things that you learn, normally when I'm teaching a class, any class, even when I'm teaching Lafern, I teach her more than most of you. I show her the first example, she's a little iffy. By the time she sees the third one, she's good. And that's how it is with me in math. That's why I normally give more than one example. 1, 2, 3, 4. The first one, confuse the daylight out of you. Second one, you see a pattern, you say, oh. Third one, no, I'm gonna get it now, man. Lafern is like that with me. Anthony sometimes gets it from the first, but he might get it from the second this time. And Jermaine, you are like me in a particular class that I did at UA. Man, come and chat some phone shit, man.
Repeat that, sir.
Like Spanish to me. So you are like how I was in a particular class at UA. The teacher come and it was like he was talking Spanish. You can take
Okay.
about 5 examples and you're good. Once you get it, you don't forget it. It's a good thing. Michaela,
Okay,
I can't read her on now. I don't know when she understand, when she don't understand. She don't talk. But I can read the next three of you. If I were in class right now, I wouldn't know if you understand or not. But Michaela, I have no clue. I remember one time I was teaching a class with Michaela. Michaela, I think it was me, Laffer, Michaela, and it was me, Laffer, and Michaela. And I'm teaching Michaela, get up and walk, how much your business. Laffer laugh, she laugh, she laugh, she laugh. Really? Everybody's different. Any questions? Probably they're laughing now because I bet you remember. Laffer, let me hear your voice.
How you do that?
I don't know why you're laughing, man, because that child can laugh, you laugh. Michaela, are you here? She probably walk gone again, you know.
How come I miss that